Okay, welcome back, grade 9. We're going to be moving on to Unit 8 now, which is all about three-dimensional measurement calculations. And I'm just going to remind you about our staircase to success. I totally recognize it's more difficult trying to learn something via distance. Challenges for both of us, challenges for me learning how to use YouTube. There'll be challenges for you, but I totally believe that we can all make it to the top step. All right, so what are we looking at today? We're looking at volume. What is volume? So I'm going to start by talking about something that's one-dimensional, length. What is length? It's a linear measurement. As I mentioned, it's one-dimensional. And then you're going to pick a standard measurement. This is exactly 1 centimeter, so I made that to be 1 centimeter wide. I'll just show you that there. And when you're measuring length, you're trying to figure out how many of these would fit across from beginning to end. Now I'm not going to finish that off, but you get the idea. How many of these would fit in beginning to end? And that would be our length in centimeters. So again, length one-dimensional. That was when we were dealing with perimeter calculations in the last unit. What is area? Area is a two-dimensional measurement, and we're thinking about squares. So I'm going to take these squares and I'm going to try and figure out how many squares would it take to fill this two-dimensional surface. And then we can put more in there. I'm not going to belabor this. I'm not going to fill it all in. This is a square centimeter. And so when I'm done, after I filled all of that in, I would have my area in square centimeters. And we worked on that the last unit. We calculated areas. Now we're going to calculate volumes. What is volume? So volume is a three-dimensional measure. And notice what I have created here now is a cube. And I'm wondering how many cubes it would take to fill this. I'm not going to use the word surface now. I'm going to use solid because the word solid implies something that's three-dimensional. So I have to fill in the dimension across this way. Then I'd have to fill in the dimension coming sort of out of my computer screen. And then I'd have to fill in the dimension that's going up. And the number of cubes that fit into here, that would be the volume of this in cubic centimeters. So volume is measuring 3 dimensions. So summary, before we do some calculations, what is volume? It measures the space, the three-dimensional space contained in a three-dimensional object. Measuring in cubic, could be meters, centimeters, and the metric system. In imperial, we could be looking at inches or we could be looking at feet. And these are some of the solids that we're going to be working with on this particular unit. By the time this unit is done, you will know how to find the volume of all of those solids. We're going to start here. And we're going to sort of be thinking about a volume of prisms. How do you construct a prism? So we can see here's a three-dimensional solid, but it got constructed from this figure right here. And this one, this is a cylinder, it was constructed from this two-dimensional circle. So this rectangular base prism was constructed from this rectangle. So I'm going to pause and I'm going to give you some time to think about how could we do that? How could we create a three-dimensional object from this two-dimensional figure? How could we create this three-dimensional object from this two-dimensional figure? And I'm going to pause because it just is a reminder to give you time to do some reflecting. Okay, so we're back. So the way we could do it is we could take this two-dimensional solid and pull it forward through space into creating a new dimension. So you see how we've created a new dimension by pulling that forward through space. And kind of just sort of connect that back one up through there. Could do the same thing with a circle. I'm going to pull that forward through space. And then we would add the sides to it. So one way to create a three-dimensional object is to simply take a two-dimensional object and pull forward through a dimension that you're not already using. So I wouldn't pull it this way. I wouldn't start pulling this way because that's on the same plane that this is on. I need to pull forward into a new dimension. So jumping to this slide, this is sort of showing you. This is how these were created. I stacked a bunch of identical circles, and if you have maybe Mason jar lids, that little thing that you put on the top there, if you stack those, you'll see it's possible to create a cylinder. You could get a stack of index cards. That really is a three-dimensional solid, but then you can see the individual pieces that comprised it. How was it built? It was built by stacking up index cards. Now the question would be then, how are you going to find the volume of this solid? So I'm going to pause and let you think about that. We can see that we've stacked a bunch of identical circles. Then how would I find the volume of this thing? We can see we stacked a bunch of identical index cards. How would I find the volume of that thing? I'm going to pause to let you think about that. So if we think about two-dimensionally, there's a length and there's a width. Then I can figure out how much space this is taking up by finding its area. And that would be length times width. So what does that mean? That means each index card in my stack is taking up this much space here. It's taking up a length times width. So in order to figure out the volume of this particular solid, what I need to do is to figure out a way to determine how many index cards are in the stack. Because if the area of one index card was, say, 20, and I knew I had stacked 10 index cards, so let's pretend that had 10 cards in the stack, then the three-dimensional space they would be taking up would be 20 times 10, which is 200. Same sort of idea for this, especially if you stacked your mason jar lids. You can see I know how to find the two-dimensional area, or the two-dimensional surface that one circle is taking up. That would be pi times r squared. Then how many circles are in the stack? If there were 15 circles in that stack, then I would simply multiply pi r squared by 15. And that would be the total amount of space being taken up in 3 dimensions. So now the next question is, here we could simply count how many circles there are here. I haven't counted, so I don't know how many I've stacked there. But we could count how many were in the stack, and then we could multiply by that. But how would you do that when the stack looks like this? We can't tell how many circles were stacked. I'm going to give you some time to think about that. All right, so discussing this, how have mathematicians determined how many, for example, in this case, how many index cards did we stack to create this rectangular prism? How many circles did I stack to create this? And the way you do it is you measure the height of the stack. And the height of the stack must be measured in the same units that we measured the dimensions over here. So for example, if the radius was measured in centimeters, let's say the radius was 4 centimeters, then I need to measure the height of my stack in centimeters. Let's say these were measured in inches. Maybe this was 2 inches by 5 inches. Then I need to measure the height of this stack in inches. So the key idea in math now is that the height of the stack is going to represent the number of two-dimensional shapes that were stacked. And if I want to find the volume, I'm simply going to take the area of my base shape. In this case, it was an index card, a rectangular index card. In this case, it was a circle. And then I'm going to multiply by the height. I'll just put an S there, the height of the stack or the height of the prism. And again, now why did that make sense? We said, I know the area of one index card. Maybe I'm going to change this over here just so it matches our previous numbers we were working with. Let's erase that. Let's come back. Let's put 4 inches here. So we've measured 4 inches by 5 inches. That gave us an area of 20. And the units here would be inches squared. And then we said if there were 10 index cards in the stack, the total amount of space they were taking up three-dimensionally, it would make sense to multiply the area of the base here by the number of cards. And now we're saying the number of cards is just going to become the height of the stack. So we're going to formalize that on the next slide. That previous slide was just to give you some insight into why the formula works. So if you want to find the volume, and here I'm going to say this is of a prism, and perhaps I didn't discuss what a prism was, so maybe I will do that on this slide. If you want to find the volume of a prism, it's the area of the base times the height. Now, how do you create a prism? So over here, we created these prisms by stacking identical shapes on top of each other. So coming back over here, that's my summary. So what did we stack here? We stacked identical pentagons. And you can tell you are a prism if this base here on the top is identical to the base on the bottom. If it's smaller, then you're not a prism. Here we were stacking hexagons, and this hexagon here on the top has to be the exact same. It has to be congruent, not even the same area. It has to be absolutely congruent. This shape here is congruent to this shape, then we've created a stack of them. Then this is definitely the definition for prism. Over here we were stacking triangles, and again the triangle on the top must be identical to the triangle on the bottom. And in this particular case, it looks like we were stacking squares. Same philosophy. This square has to be identical to the square here, and in this case stacking circles. And over here it looks like we were stacking rectangles. There's the rectangle on the top, rectangle on the bottom. So how can you tell if you're a prism? You need to be stacking identical shapes. How do we find the volume of the prism? We're going to find the area of the base. There's a base in this case, and in that case, and in that case, in that case, and so on. Find the area of the base, and then there's the height of the stack. This is how many circles I stacked, how many pentagons, how many hexagons, how many triangles. And then we're going to move to the next slide, and we'll take a look at some examples. So on this slide, how do you find the volume of a prism? Remember, the volume of a prism is equal to the area of the base, a bit longer, area of the base, times the height of the stack, or we could put a P there for prism. So you're going to start on A. The first thing I need you to figure out is what got stacked. Is this a prism? If it's a prism, you should be able to identify the two-dimensional shapes that were stacked on top of each other. And then you're going to plug into the formula area of the base times the height of the stack. I'm going to pause so you can do that work. Okay, moving forward, we can see that what we've done is we sort of stacked this arrow shape. And I'm going to stack, and I'm looking at it going backwards into my computer screen. So what I've done is I've stacked a bunch of identical arrows. How do you find the volume of a prism? I've established I do believe it is a prism. I'm just going to show you. There is the arrow on the back end. And the arrow on the back end is identical in size to the arrow on the front end. Absolutely identical, congruent. So we know it's a prism. How do you find the volume of a prism? It's the area of the base times the height of the stack. Over here, they've given me the area of the base. They told me it was 32 square inches. And over here, they've given me the height of the stack. So I've plugged in those numbers. There's the area of the base. There's the height of the stack. Whoops. And there's the height of the stack. 32 times 5 gives me 160, and now our units will be inches squared. And the reason that's happening is because we've taken inches squared from here, and I'm multiplying that by inches over here. And altogether, these two will combine. Inches squared times inches will give me inches cubed. So now that you've seen how that works, identify the identical shapes that are being stacked. Confirm for yourself that it is a prism. And if it is a prism, then you can use the volume is the area of the base times the height of the stack. Again, I'm going to pause so you can do some work on this one. All right, so moving forward and looking at this next solution, I can see that what was stacked were hexagons. And the hexagon on the top here is exactly identical to the hexagon on the bottom, thus creating a prism. How do you find the volume of a prism? We use the formula area of the base times the height of the stack. Now I'm going to do the area of the base in purple, so there's the area of the base. I'm going to plug that right in for the area of the base. I'm going to use green for the height of the stack. The height of the stack is 6. Plugging that in there. 21 times 6 gives me 126 cubic centimeters. And again, why cubic? Centimeters squared times centimeters here gives me cubic centimeters. Please make sure you have the correct units. And now you're going to try the last one. So I'm going to pause to give you some time to think and reflect. All right, so we're back. Now let's take a look at this solution. So what has been stacked here are identical trapezoids. I got a trapezoid on the front, and then we've got a trapezoid at the back. These two trapezoids are identical, and then the stack is heading back into the screen again. So confirm that this is indeed a prism. How do you find the volume of a prism? It is once again the area of the base times the height of the stack. The area of the base is right here. They told me that was 12. So I plugged that in there. They've given me the height of the stack over here. The height of the stack is 2. So I'm going to plug that in right there. 12 times 2 is 24. And now we have the volume of this trapezoidal prism is going to be 24 cubic meters. Again, the units need to be cubed because in areas and square units, we're multiplying by a linear measure. The height will be a linear measure. Meters squared times meters gives me meters cubed. All right, on to the next slide now. What I would like you to do on this slide is we're going to drag formulas over, and then maybe we'll take a look at where's the area of the base versus where is the height of the stack. So I'm going to pause in a few minutes, and what I would like you to do is drag the name to the name of the shape. Actually, I don't think we should call that shape. I think solid is a better descriptor of this, so I'm going to change that to solid. So drag the name of the solid over and drag the formula over. I'm going to pause to give you some time to think about that. All right, so moving forward, this is a rectangular base prism. There's our cylinder. There's our triangular base prism. This one's a cube, and this one's a square base prism. And we did say that the volume of any prism is the area of the base times the height of the stack. So I think I'm going to do these in different colors. So let's do area of the base. And then the height of the stack I'm going to leave in blue. And then I'm just going to come over here. I'll change the thickness of that pen for a sec. And coming back over to here. All right, so coming over to here, the base right here is this rectangle. And so there's the formula for the area of the base, length times width. The base here is this circular. I guess the base there is circular. The base is a circle. And right here, see if I can do that with my mouse effectively, there's the formula for the area of the base. So area of the base times the height, area of the base times the height. We are still making use of this formula. This is a triangle here. And in this formula, to avoid confusion, rather than writing an H for the height of the triangle, which could be confused for the H, which is the height of the prism or the height of the stack, they're using the letter L here. So L is representing the height of a triangle. The formula for the area of a triangle is 1/2 base times its height. And the height of the triangle in this case is L. So again, still using the same formula. Coming over to the last one, the cube, there's the base. The base in this particular case is a square. To find the area of that squared, it should be W times W. So we'll break this one up a bit into W squared. Then I'm going to grab the blue pen times W. And then over here, there's the area of the base. In the square base prism, it's easier to see because the area of that square is W squared. So notice how all of these formulas are still using area of the base times the height. All right, moving on to the next slide. All right, now you're going to make some volume calculations. These are a bit different from the previous ones they did here because in these cases they actually gave you the area of the base. In these ones you're going to have to find the area of the base. You can do them in 2 separate steps if you want. Like sometimes I've had students who would off to the side write area of the base equals, and then they would work that out, and then they would move on to volume in the next step. Or you can just go straight into the formula. All right, I'm going to pause so you can work on the first one. All right, so taking up this first example, this definitely is a prism. We were stacking squares, and I'm seeing the stack is moving up this way. The formula for the volume of any prism is area of the base times its height. The base here is a square, so I could plug in the formula W times H. The area of the base now part, which I'm going to do in just this green here, that's the area of the base. This is the area of the base, is going to become 9 times 9. And now the height of the stack, which is right here, being plugged in here, is 8. And 9 times 9 times 8 gives me 648. And of course, my units are going to be centimeters cubed because we did centimeters times centimeters times centimeters times centimeters. All right, I'm going to give you some time to work on the next one now. All right, so looking at this next solution, this is actually a cube, but notice the base here is also a square, as it was in this one. So using the formula area of the base, which I'm going to highlight in purple, is now going to be the W times W. These two are equal to each other, so I'm using the same letter here. Multiplied by the height. I'm using this to be the height here. That's also a W because they were all the same. So I simply could have used the formula W cubed rather than W times W times W. All of these measures are 7, and 7 times 7 times 7 gives me 343. And again, units would be centimeters times centimeters times centimeters, and that gives me my centimeters cubed. All right, next slide. You're now going to find the volume of this one. I'm going to pause so that you can do the work. I'm recommending, of course, that you do pause. All right, so looking at the solution to this one, circular. The base is a circle, and the height of the stack is coming down this way. So that's the height of the stack there. Because the base is a circle, I need to know what the radius is. And the radius, this gave me the diameter here, so I need to remember to work with the radius. 7 divided by 2 is going to be 3.5, so the radius of the circle is 3.5. So for the area of the base, I'm going to be using the formula pi r squared. The radius is 3.5, so I'd plug in the 3.5. The height is right here, this dimension right here. That's 8.5 centimeters, so I'm now going to plug in the 8.5 here. I'm going to punch all of this into my calculator. Pi times 3.5 squared times 8.5, and that gives me the value 327.12. And the units, once again, centimeters cubed, because centimeters times centimeters times centimeters. All right, now one last example. And again, I forgot to mention at the beginning, I do know this is a prism because I'm stacking identical circles. You should convince yourself first that it actually is a prism, because tomorrow we're going to be adding a different solid. It's not going to be a prism. And eventually we'll add a third different type. So it's useful if you can identify the types. I'm going to pause so that you can figure out the volume of the next one. All right, so looking at the volume of this last shape, I should make sure or ensure that this is indeed a prism. So I've got a triangle, and identical triangles have been stacked. The triangle on the top is the exact same size as the triangle on the bottom. So this is definitely a prism. I'm going to be using the formula. Volume is area of the base times the height. The base in this case is a triangle. So now I've written 1/2 base times height of the triangle. The slide I showed you up here, they like to use the letter L instead. But I am fine with making a distinction, putting height of the triangle, and now I wrote height of the prism, because the height of the prism is going to be this one right here. Or we can write height of the stack. So that's the height of the prism. So the formula sheet that EQAO uses, but we're not writing EQAO this year anyways, they'd like to put an L there. All right, so now what do we have here? I'm just going to flip this triangle on its side over here, just so that you can see. That is here, so there is 12. The 5 is going here, and there's a right angle there. The reason I did that is so that you can see this is a base height pairing. So I'm going to use 12 for the base of my triangle, and I'm going to use 5 for the height of the triangle. And there's the, I'm writing that as 0.5, but that's base times height divided by 2. It's the same thing as 0.5 times base times height. They're identical to each other. And now the height of our prism. is the 20 right here that I already mentioned. So I'm going to plug that 20 in. And then into my calculator, I'm going to do 0.5 times 12 times 5 times 20. That's going to give me 600. This time the units become meters cubed because we have meters times meters times meters. And that gives us meters cubed. All right, one last thing to look at for today. I got this off the NASA Glenn Research Center. This is the formula they are using for the volume of the cylinder. And in fact, we were using area of the base pi r squared times h. They're using this formula. And what I would like you to decide, is that formula correct? And note, we can write this as pi d squared over 4 times h. So there is the area of the base, and here is the area of the base. So I guess the question I'm asking you to think about now, is pi d squared over 4, is that a correct formula for the area of a circle? I'm going to give you some time to think about that. All right, so finishing this off, I moved to a new slide to show you this. So the area of a circle, we are familiar with using pi r squared. But remember, the diameter is equal to 2 radii. 2 radiuses and 1 diameter. That means there is half a diameter in 1 radius, which I could write as diameter over 2. So I'm going to go into the formula pi r squared, and instead of writing r, I'm going to replace r with half the diameter. That's correct. And now diameter over 2 all squared, I'm going to write that out in long form. That means diameter, half the diameter, times half the diameter. So instead of writing it as squared this way, I'm going to write it in long form. And then I need to multiply these two together. D times d is d squared. 2 times 2 is 4. So d over 2 all squared is the same thing as d squared over 4. And now I have pi times d squared over 4. And on this previous slide, we just said, well, if we could verify that pi d squared over 4 was indeed the area of a circle, we'd be done, which we have. Now I'm just going to plug back into here to show you that the formula for the volume of a prism is area of the base times the height. We've now determined that we could write the area of the circle as pi d squared over 4, and this is over 1, and this is over 1. So the numerator is pi times the d squared times h, and 1 times 4 times 1 is 4. So this is indeed an alternate way to find the volume of a cylinder. And I think that's going to be it for today. Again, thank you for watching. Hope you found this video useful. Don't forget to like and subscribe, and we will see you tomorrow. Take care.